Okay, so let's see. Okay, so we're trying to use a kernel with SPM, right? SPM so kernel use kernel. Hey, okay, so in SPM we can use a version of the same idea to motivate the need for kernels, right? So let's look at some data that is not linearly separable. Right? It's your data. If you look over here in this case, see, now we're trying to fit I think did I miss something here? Okay, let's try again. Okay, see, okay, it's fine. So we're trying to fit a non-linear. You're saying where you know, circular elliptic data sunny. So it's good discriminating length, of course, is okay. So we cannot discriminate, or we cannot, separate them using a straight line, of course. And a straight line use sum of top type, right? So we tried it, right? And we try got you. It's nowhere near. It's nowhere near, right? Okay. So you the question. Classification, does it work? No, right? So it's not working at all, right? Using the good of course, right? So it is clear that no linear discrimination will ever be able to separate this data. But we can draw a lesson from the basis function regression, right? And think about how we might project the data to a higher dimension such that a linear separator would be sufficient, right? For example, one simple projection that we could use would be to compute a radial basis function centered on the middle clump. Means of ambiguity. So I'm just linear regression, linear model, and linear regression use गर्दाखेरि हामीले के गरेका थियौं भन्दाखेरि डेटालाई अर्को डिमेन्सनमा लिएर गएर है हायर डिमेन्सनमा लिएर गएर चाहिँ हामीले त्यहाँ चाहिँ we were able to fit like basis function, like you guys are familiar with basis functions, right? So this the how the basis function we're going to use a basis function here, okay, which is this one, radial basis function, right? Okay, radial basis function means it's called some center is it's the circular elliptical data, radial. So your radial coordinates, radial coordinates, it's a Cartesian coordinate for you. X, Y, this is any Cartesian coordinate system, and you see radial coordinate. Just like this one, gives the angle. Angle is good. Some city center and angle butter, and you see your position determining also. Okay, so this is a radial. That's the radial. Okay, so we create a function, something like this, which is this function right here. Right? R is equal to e to the power minus x squared, and this go, and then we sum, right? Sum that, right? Okay, and then sum one, so your x is 1. Right? So now, all right, so we can visualize this extra data dimension using a 3-dimensional plot. Okay, so let's see. Let's see. I don't know if we my mirror. Graphics support not okay. So it's much of a 3D. It doesn't quite show me 3D. It still is 2D. Okay. So okay, not much to be inferred from here, but you can skip that. Don't worry. Right. So all right. So now let me run this. So I'm looking also doing you say the right? So you say unfortunately graphics support right? So okay, so this thing. So what we do here is this: we create a classifier. Where the kernel, okay? We're using the kernel RBF kernel. Right? RBF can you guess what is RBF?
Radial basis function.
Yeah, that's right. Sir, radial basis function. So I'm going kernel key use radial function basis function. It will create a radial basis function of something similar to this. Right? Okay, so that is the radial basis function. And then we use again we use c equal to a big number, right, to the power 6. Right? A big number, right? Okay, and then we fit that. So basically, we fit our x and y, right, through this xy means this xy using circular data set. Okay, now I'm xy change by it. So your data xy data, right? So we send it through our fit, right? We train our model. I train our model on this, this circle looking data, right? The nonlinear data. Okay, we run, okay, we fit here and fit garchau xy. It's not that समाथिको xy हैन, यो xy जुन यो concentric circle भन्छ नि, है त्यस्तो खालको data. So त्यसमा गरेर हैन, अनि त्यसपछि when you plot it, यसलाई plot गरेर है त, let's see. This is the problem, right? So let me run it again. Try again. See right here. Okay, nice fit, excellent fit, right? See, perfect, almost perfect. Understand? Right? So now this is the these are the margins, right? Margin. They have ठ्याक्क जुन अघि सीधा थियो नि त्यसलाई अब कर्भ भएर ठ्याक्क एउटा है सर्कल क्लोज लुप बनाइदियो. Okay? Okay? So now instead of being straight, you're straight, right? You say of a circular. Right? The whole thing is circular. Right? And then it gives you perfect fit. Have you considered some of that? Okay, can you tell me the process how we got here? Understand?
Higher dimension change
some kind of a basis function line. Input ma basis function लगायो हैन, अनि जुन कि रेडियल बेसिस फंक्सन त्यसले चाहिँ के गर्यो भन्दाखेरि अर्को कोअर्डिनेटमा लिएर गयो है, त्यसले चाहिँ त्यो डेटालाई अर्को कोअर्डिनेटमा लिएर गयो हैन, रेडियल बेसिस फंक्सन. सो मेबी रेडियल कोअर्डिनेट अर सम अदर स्पेसमा लिएर गयो कि अर्को स्पेसमा लिएर गयो है. ओके, हैन, रेडियल बेसिसमा लिएर गयो है, अर्को बेसिसमा लिएर गयो, अर्को वर्ल्डमा लिएर गयो हैन. उले चाहिँ के गर्यो भन्दाखेरि त्यो हाम्रो डेटालाई उले ट्रान्सफर्म गरेर उले चाहिँ अर्को वर्ल्ड, अर्को कोअर्डिनेट, अर्को बेसिस भन्छ हामीले हैन, अर्को बेसिस भनेको अर्को वर्ल्ड, द्याट्स अ डिफरेन्ट वर्ल्ड हैन. त्यहाँ लिएर गएर अनि त्यहाँ चाहिँ के गर्यो भन्दाखेरि त्यहाँ लिएर गएर अनि उले चाहिँ के गर्यो भन्दाखेरि उले चाहिँ यही नै है, उले चाहिँ सपोर्ट भेक्टर क्लासिफायर है त्यही नै युज गर्यो है. त्यहाँ नट इन द यो वर्ल्डमा हैन, त्यो वर्ल्डमा अर्को हाई डिमेन्सनल वर्ल्ड हैन, त्यहाँ गयो, त्यहाँ चाहिँ पर्फेक्ट फिट भयो है. त्यहाँ चाहिँ किनभने त्यो डेटा यसरी चेन्ज गरियो कि त्यो त्यसले त्यहाँ फिट गर्न सकोस् है, बुझ्नुभयो? त्यो डेटा यसरी चेन्ज भयो त्यो अर्को वर्ल्डमा, डेटालाई हामी यसरी चेन्ज गर्यो कि ताकि हाम्रो नर्मल सपोर्ट भेक्टर क्लासिफायरले त्यहाँ मजाले क्लासिफाई गर्न सकोस् है. ओके, भनेपछि त्यहाँनिर पर्फेक्ट क्लासिफिकेसन भयो हैन त्यो वर्ल्डमा है, त्यो अर्को वर्ल्ड है. ओके, अनि त्यहाँनिर फिट भइसकेपछि अब हामी त्यो मोडललाई ठ्याक्क हाम्रो यो वर्ल्डमा लिएर आउँ है, यो वर्ल्ड लिएर आउँदाखेरि अनि यो फर्ममा आउँछ है, जुन कि अर्को वर्ल्डमा यही कुरा के हुन्छ, स्ट्रेट हुन्छ है, अर्को जुन बेसिसमा नेक्स्ट है, जुन अर्को बेसिस छ नि, अर्को बेसिसमा यही कुराहरू सबै स्ट्रेट हुन्छ र डेटा पनि त्यही अनुसार चाहिँ उता त्यही अनुसार चाहिँ यस्तो डेटा हुँदैन डेटा, किनभने हाम्रो डेटा चेन्ज भइसक्यो है उता है. सो काइन्ड अफ मेक्स सेन्स है. अलिअलि बुझ्नुभयो?
हजुर सर.
So yeah, I mean it might be just the linear algebra मा जुन बेसिसहरु यो पढ्नु भयो भने, I mean so त्यसले गर्दाखेरि यो तपाईहरुले linear algebra को बेसिक्स हैन, बेसिस linear algebra को हैन, सो यो कुराहरु त्यो भयो भने चाहिँ it will be much easier के तपाईं त्यो कन्सेप्चुअली बुझ्नको लागि. So it's all data science, machine learning, it's all based on statistics and probability, linear algebra, calculus, यो सबै छ के हैन. अब तपाईले त्यो नबुझे पनि तपाईले काम गर्न सक्ने होइन हैन, तर तपाई जति त्यो डिपमा डेप्थमा बुझ्नुहुन्छ तपाईको क्ल्यारिटी त्यति नै आउँछ कि है, त्यसले चाहिँ इट मेक्स अ डिफरेन्स. अब आजकल त यु डोन्ट ह्याभ टु हैन, तपाईको त्यो म्याथमेटिक्स थाहा नभए पनि यु क्यान स्टिल बी हैन, यु क्यान स्टिल वर्क हैन as a machine learning engineer हैन. But if you want to get that clarity, and you need to have those I know the concepts are important. Okay, so anyway, so this is how it works. So I'm radial basis function use guy, right? Okay, so using this kernelized, so there's a kernel, right? Basis transformation, there's a kernel, and you see radial basis function, there's a kernel. Okay, that is a kernel. So let's have a kernel methods function, right? So using this kernelized support vector machine, you can learn a suitable nonlinear distance boundary. Okay, this kernel transformation strategy is often used in machine learning to turn fast linear models into fast nonlinear models, especially for modeling in which the kernel trick can be used, just like SPM. Right? Okay, so which is, see, it's spectacular. The results are astonishing. Okay, see, with very little transformation or little, little bit of work, just a little bit. Okay, maybe one line, maybe, I know. Okay, so it's really, really amazing. Okay, let me try go you. Let me take your attention. See, get a snapshot in that. Okay, 1 second. Okay, here we go. Save it. Here we go. All right, so now let's get back. Again, C was set to a very big number, right? What is C? Okay, let's look at what is C, right? So tuning the SPM, softening margins, right? So so far, our discussion has centered around very clean data sets in which a perfect distance boundary exists, right? But what if your data has some amount of overlap, right? For example, you can have a data like this. I used to have data. So see, yeah, clean separation China. There's no way you can, cleanly separate these. There's no way you can cleanly separate these two classes, right? So to handle this case, the SPM implementation has a bit of a force factor, right? Force factor, right? Which softens the margin. That is, it allows some of the points to creep into the margin. Okay, if that allows a better fit. Okay, so it allows some of the points to creep into the margin if that allows a better fit. The hardness of the margin is controlled by the tuning parameter known as C. Right? C. If you remember, C का value को देखते हो last time. Do you remember?
1 to the power 10, 10 to the power
60. Right? Okay, 1e60. Right? 1e6 भनेको 10 to the power 6. Right? 10 to the power 6, which is 1 million maybe. Right? So it's a big number, right? So that means it's hard because it's a big number. So the margin is really hard. It's a hard margin, a hard margin. Okay. So you see, like, if we can somehow, so if we give a smaller number, if a C, now our margin becomes softer and softer. Okay. So for a very large C, the margin is hard, as you saw, right? For a very large C, the margin is hard and points cannot lie inside of it. Right? We didn't let the points cross the margin. Right? Marginal cross right? But for smaller C, the margin is softer and it can grow to encompass some points. Okay, so let's see. Let's try this. Your case, now we can let, okay, so stay isma. So if you put margin C equal to 10, C equal to 10, you are hardly letting 10 is still a, comparatively a bigger number. So this one say the points are your margin with the series side. So it's my case. See, you're letting the points get into the margin, right? See, so 0.1 is it, you're letting them go inside the margin. Okay. So this thing, we have some some of these examples here. For example, face recognition. Okay, let's quickly try this thing. So how can you use how can you use SVM, right? Support vector classifier or support vector machine in face recognition, right? Let's quickly try to take a look at it. Okay, so let's take a look at facial recognition problem. We'll use level faces in wild data set, which consists of several thousand collated photos of various public figures. Right? So first one, we okay. So it might take a while to load and everything. So I won't run. It probably runs, so I'll just let me see. Okay, let's try. Yeah, so anyway, so let's try it. So we run this. Yeah, good. So we fetch the data set, environment now. Let's run it. Okay, very good. So now you can see this is the data set where we have the picture and the name, right? Picture name, so you label data sets, right? This is a label data set where, you know, so it says the Donald Trump spell, right? George Bush, see Ariel Sharon, Israel, right? Colin Powell. These are they're famous figures, right? Famous faces, right? All right, so each image contains 62 by 47 or nearly 3,000 pixels. Right? We could proceed by simply using each pixel value each feature, but often it is more effective to use some sort of pre-process to extract more meaningful features. Okay, we can use principal component analysis. See, it's a high-dimensional data. So, picture 62 by 47, right? 62 by 47 pixels. Means if you flatten it, 62 times 47, 3,000 pixels. Okay, but if you see hamro x katiba, harek pixel is x, x1, x2, x3, x4, right? And you see 3,000 or out, and you will see harek picture is how many dimensions? Almost
3,000.
3,000 dimensional, right? 3,000 dimensional. So first map is always a good idea to keep it. Reduce the dimension. And this na we can use principal component, which is a detail I am your person, don't worry. A principal component analysis we reduce the dimensionality of this 3,000 dimension, and let's bring it down to 150 fundamental components. Right? Except plus the 3,000 dimension except plus dimension. Right? And data let's run it through a support vector machine. Right? SVM classifier, right? SVC, right? Okay, so let's see. We can use a pipeline, right? We can create a pipeline. Okay, so I'm looking at SVC, of course, and then PCA. Okay, and this was we make a pipeline and but a PCA. Right? We instantiate PCA with 150. Right? We want to bring the data to 150. I mean, bring the dimensionality to 150. Okay, why didn't we ignore that one in random state? Okay, you randomly custody. Right? So don't worry about this one. Main comments are you, okay, and components to go 150. Okay, so any SVC we use radial basis function. Right? Radial basis function use also. Okay, balance weight. And simply we make a pipeline. Our data goes through PCA, and this output is SVC. Right? So I don't have to draw. I've already drawn a lot of the pipelines. And first one PCA, right? Input first answer, input came answer, PCA answer, PCA ko output see, SVC ko input bunch. Right? Pipeline. Okay. All right. So now let's see. I'm looking at let's split our data to test and train. Right? Train and test. Right? So you guys know this, right? Train and test. 75-25 mouse, right? By default. And this, let's see what we can. Did I run that? Did I run it? No, right? Let me run that one. Okay, very good. Obviously, I'm grid search. You guys know grid search, right? We've already covered grid search, right? And it's a grid search. It's the C value 1, 1, 5, 10, 50 is सबैमा test गर्छ भने है अनि gamma को value right? So यसरी gamma चाहिँ उसको हैन radial basis function को त्यसको हैन. Okay, so now this parameter, okay, hyperparameter. Okay, so you given a combination, हरेक combination try गर्छ. So we have 4 1 2 3 16 वटा हैन, 16 वटा possibility सबैमा टेस्ट गर्छ भने हैन, सबैको भ्यालिडेसन है, भ्यालिडेसन स्कोर दिन्छ. अनि त्यसपछि के हुन्छ भन्दाखेरि we do अनि त्यसपछि हामी ग्रिड सर्च सिबी गर्छौं है, जसमा कि we model a param grid है, यो ग्रिड दिन्छ, हामी मोडल दिन्छौं. यहाँ गएपछि now this will search for the best combination of C र gamma. C र gamma को best combination. Well, 16 वटा है, 4 4 16 वटा combination, different combinations are try गर्छ हैन. र जुनमा चाहिँ best हाम्रो validation score आउँछ नि हैन, it will report that. Hey, so let's see. So हाम्रो best score के आउँछ, let's see then. Okay, let's see. Okay, model. Okay, so very good. Model, when you see your model, right up here, the pipeline, and then pipeline. Okay? Yeah, there you go. So, right? So yeah, it'll take a while because there's a lot of data, lot of, so processing to be done. Okay, let's see how long it's gonna take. Okay, so I think it's gonna take a while. Oh, you're saying, of course, when I don't have GPU like fast हुन्छ हैन, मेरो सिस्टममा GPU छैन है. So the Colab मा चाहिँ GPU हुन्छ अनि we can use GPU ले एकदम फास्ट गरिदिन्छ है. अब अहिले actually GPU programming, parallel programming, GPU programming, so त्यसको एकदमै है demand of more and more machine learning are done on GPU है. It's all specialized hardware right? So okay, let's see. Big data ठुलो हैन, particular mirror machine को लागि चाहिँ it's a bit okay. Anyway, so you run with us, man. We can probably look down here. What we got here, right? Okay, so the run the optimal values fall towards the middle of our grid if they fell at as we want to expand the grid to make them. Okay, so let's say best estimator, the best combination this one predict garchau using the this grid called model of best estimator right. अनि त्यसपछि हामी त्यसमा प्रेडिक्ट गर्छौं अनि हामीले के गर्छौं है, अनि यसको टेस्ट गर्छौं है, टेस्ट गर्दाखेरि अफ कोर्स इट्स के बेस यतै सीपीयू मा धेरै टाइम लाग्छ के. Okay, so okay, anyway, so let's see if तपाईले यसलाई तपाईको Colab मा रन गर्नु it will be much faster. Colab मा, but make sure that you're selecting GPU as runtime. Right? Okay, anyway, so sorry. So anyway, it works very well. Right, so okay, so you can read the summary and all those. Right? So okay, anyway, so looks like it's going to take a long time. So okay, so basically, yeah. And now you have a clear, you have an idea of what server vector machines are. Right? Okay. All right, so okay, so as right? Let's just do this much today. So tomorrow, let's see about kati baki cha ta. Okay, let's see. So support vector machine that's about it. So next we're going to cover random forest, and this is principal component analysis and k-means. Okay, and that's what I plan to cover. Right? So other three, right? 3 classes now. I think we'll finish. Okay, okay. So main you can work on your. I mean, you can follow on your own. I've already provided you the this these links to. I mean, there's all this, right? So so I'll cover the main. This machine learning. We have come a long way in machine learning. Machine learning, you may not realize it, but very advanced, very crucial components, core components, crucial components, crucial fundamental ideas, fundamental concepts, right? We have gone through them, right? So you have provided you have done your work, right? Like class was shooting export that's not going to happen. So it's a minute. मेहनत नगरिकन के पनि हुँदैन तपाईको मेहनत नगरिकन हैन सो तपाई जति मेहनत गर्नुहुन्छ त्यति नै तपाई पाउनुहुन्छ नि त हैन the more effort you put in, the more time you put in, the more तपाई जति लागि पर्नुहुन्छ त्यति नै तपाईले रिटर्न आउँछ के है रिटर्न अन इन्भेस्टमेन्ट है सो तपाईले इन्भेस्ट नै गर्नु भएको छैन भने तपाईको प्रफिट आउँछ मतलब तपाईको do you get revenue no right so त्यही हो it's all depends on you तपाईँ आफैमा डिपेन्ड गर्ने कुरा हो हैन so I suggest कि तपाईहरु हैन so please I can turn off the recording probably